spacecraft with tiny payloads to Alpha Centauri, the nearest star system, traveling at up to 20% of the speed of light. The spacecraft would be so small, weighing only a few grams, attached to sails just meters across but thinner than a human hair. Ground-based lasers, combined to create 100 gigawatts of power, would push these tiny craft to velocities that would allow them to reach another star system in just over 20 years. If humanity could build such technology with our relatively primitive capabilities, Loeb reasoned, perhaps more advanced civilizations had mastered it long ago. Perhaps they had sent their own probes across the galaxy, their own scouts to explore distant stellar systems. And perhaps Oumuamua was one such probe, either still functional or long dead, drifting through space like cosmic flotsam. A derelict light sail from a civilization that might have flourished and faded millions or billions of years ago. The mathematics supported this possibility. For Oumuamua's observed acceleration to be explained by radiation pressure alone, the object would need to have an extraordinarily high surface area-to-mass ratio. It would need to be, essentially, a sheet, less than a millimeter thick, yet potentially hundreds of feet across. The numbers worked out remarkably well if you assumed it was something like a sail. Such an object would be accelerated by sunlight in exactly the pattern that was observed, following that precise one over R-squared relationship as it moved away from the sun. And there was precedent for such thinking. Throughout history, when we have developed new technologies, we have naturally wondered whether others might have developed the same technologies. Once we invented radio, we began searching for radio signals from space. Once we built lasers, we looked for laser communications from other civilizations. It was entirely natural, Loeb argued, that once we began seriously developing light sail technology, we might wonder whether light sails from other civilizations had ever visited our solar system. His 2018 paper with Shmuel Bayali, published in the astrophysical journal Letters, laid out the case methodically. The paper didn't claim definitively that Oumuamua was artificial. Rather, it proposed that the light sail hypothesis deserved serious consideration alongside natural explanations. It was a hypothesis that fit the observations, that required no new physics or chemistry, only technology that we ourselves were already developing. In the rigorous language of scientific papers, they concluded that Oumuamua's properties were consistent with an artificial origin. The reaction from the scientific community was swift, and in many cases, harsh. Headlines around the world proclaimed that Harvard scientists thought Oumuamua was an alien spacecraft. The nuance of the actual paper, its careful language and measured conclusions, was often lost in the excitement and skepticism that followed. Many of Loeb's colleagues felt he had crossed a line, that he was speculating too wildly, that he was giving credence to ideas that belonged more in science fiction than in serious astronomical research. The intensity of the response revealed something about how science operates, particularly when it comes to controversial topics. Within days of the paper's publication, astronomers around the world were weighing in, many dismissing the light sail hypothesis without, Loeb noted, having actually read the paper itself or engaged with its specific arguments. The criticism often focused not on the technical details or the mathematical calculations, but on the very premise that such a hypothesis deserved consideration. It was as if there existed an unspoken rule that certain ideas, no matter how well they fit the data, simply shouldn't be discussed in polite scientific company. This reaction puzzled Loeb. In his view, the light sail hypothesis was actually quite conservative, compared to some of the natural explanations being proposed. After all, light sails were real technology. We had built them. We knew they worked. Japan's Ikaros spacecraft had successfully used a light sail to travel to Venus in 2010, demonstrating that photons could indeed propel a spacecraft through space. The Planetary Society's LightSail 2, launched in 2019, had successfully raised its orbit using only sunlight for propulsion, providing additional proof of concept. If we could build light sails with 21st century technology, requiring no new physics or exotic materials, why was it so implausible that another civilization might have done the same? Why was it more scientifically respectable to propose never-before-seen types of ice or entirely new classes of cosmic objects than to suggest that another technological civilization might have developed technology similar to our own? Moreover, Loeb argued, the light sail hypothesis made specific, testable predictions. If future, interstellar objects showed similar characteristics, if we detected more anomalously thin, flat objects with high reflectivity and non-gravitational acceleration, that would strengthen the case. If we never saw such objects again, if Oumuamua proved to be truly unique, that would weaken it. The hypothesis was falsifiable, which in scientific terms meant it was legitimate science, not mere speculation. The debate also touched on deeper questions about the nature of scientific inquiry. How do we balance skepticism with open-mindedness? How do we evaluate extraordinary claims when the evidence is limited but suggestive? These are not trivial questions, and they don't have simple answers. The history of science shows that both excessive skepticism and insufficient skepticism can lead us astray. Being too quick to reject new ideas can cause us to miss important discoveries. Being too quick to accept them can lead us down paths of error and wasted effort. Carl Sagan's famous dictum, "Extraordinary claims require extraordinary evidence," is often invoked in debates like this one. But what constitutes extraordinary evidence? And doesn't the assessment of what counts as extraordinary depend on our prior assumptions? If you believe that technological civilizations are extremely rare, perhaps unique to Earth, then any claim of an alien artifact will seem extraordinary indeed, requiring near-perfect evidence before you'll accept it. But if you believe that life and intelligence are common in the universe, that technological civilizations are abundant in the galaxy, then encountering one of their artifacts doesn't seem so extraordinary. It becomes a question of statistics and probabilities rather than philosophical impossibility. Loeb pointed out that we're willing to entertain all sorts of exotic ideas in astronomy. We believe in dark matter, an invisible substance that has never been directly detected but whose existence we infer from gravitational effects. We believe in black holes, regions of space-time so warped that nothing can escape them, objects that seemed absurd when first proposed. We believe that the universe began in a Big Bang, that time itself had a beginning, that space is expanding and carrying galaxies away from each other at ever-accelerating rates. All of these ideas seemed extraordinary when first proposed, yet we've come to accept them because the evidence, while indirect, is compelling. Why, then, was the suggestion that an interstellar object might be artificial treated as beyond the pale? The answer, Loeb suggested, had less to do with the evidence itself and more to do with social and cultural factors. There's a stigma attached to the search for extraterrestrial intelligence in some scientific circles, a sense that it's not quite respectable, that it's the domain of enthusiasts and amateurs rather than serious researchers. This stigma affects how we interpret ambiguous data. We're willing to propose exotic, natural phenomena rather than risk the embarrassment of suggesting something that smacks of UFO speculation. The criticism took many forms. Some argued that Loeb was seeking publicity, that his hypothesis was designed more to generate headlines than to advance scientific understanding. Others suggested that his involvement with breakthrough starshot had biased his thinking, that he saw light sails everywhere because light sails were on his mind. Still others felt that invoking an artificial origin was premature, that there were surely natural explanations yet to be discovered that could account for Oumuamua's peculiarities. There was also a deeper concern rooted in the history of science. Extraordinary claims require extraordinary evidence, as Carl Sagan famously said. The claim that we had detected an artifact from an alien civilization was about as extraordinary as claims get, and the evidence, while intriguing, was far from conclusive. We had a handful of observations of a small, distant object that had already left the solar system. We had no high-resolution images, no spectroscopic data that could definitively determine composition, no way to conduct follow-up observations. Drawing grand conclusions from such limited data seemed, to many scientists, deeply unscientific. Yet Loeb stood by his reasoning. He pointed out that the natural explanations being proposed to explain Oumuamua's behavior were, in their own way, equally exotic. The hydrogen outgassing hypothesis required a specific type of cosmic ray processing that had never been directly observed. The nitrogen ice theory required a fragment from a Pluto-like world to have survived hundreds of millions of years in interstellar space without being completely eroded. These explanations stretched the boundaries of known astrophysics just as much as the artificial hypothesis did, Loeb argued. They simply felt more comfortable to most scientists because they didn't invoke intelligence. This, Loeb suggested, reflected a bias in how we approach evidence. We're willing to contemplate never-before-seen natural phenomena, to propose entirely new classes of astronomical objects, rather than consider the possibility that we might have encountered technology from another civilization. This bias, he argued, was not scientific. It was cultural, even philosophical. Science should follow the evidence wherever it leads, not shy away from conclusions simply because they make us uncomfortable or because they challenge our assumptions about our place in the universe. In his 2021 book, Extraterrestrial: The First Sign of Intelligent Life Beyond Earth, Loeb expanded on these arguments. The book was part memoir, part scientific treatise, part plea for intellectual courage. He wrote about growing up on a farm in Israel, about his path to becoming an astrophysicist, and about what he saw as the scientific community's reluctance to seriously consider evidence of extraterrestrial technology. The book became a bestseller, further raising Loeb's profile and further intensifying the debates around his ideas. Not everyone dismissed the artificial hypothesis. Some scientists, while skeptical, appreciated that Loeb was at least raising important questions about how we search for evidence of other civilizations. Traditional SETI, the search for extraterrestrial intelligence, had focused almost exclusively on detecting radio signals or other electromagnetic communications from distant stars. But what if advanced civilizations didn't communicate using radio? What if they had moved beyond that technology centuries or millennia ago? What if the way to find evidence of extraterrestrial intelligence wasn't to listen for signals, but to look for artifacts, for physical objects that might visit our solar system? After all, we now know that planetary systems are common. The Kepler mission and other exoplanet surveys have revealed that most stars have planets, and that Earth-sized worlds in the habitable zones of their stars are abundant throughout the galaxy. If life and intelligence can arise on Earth, there's no reason to think it couldn't arise on countless other worlds. And if intelligent life becomes technological, if it develops spacefaring capabilities, then it seems inevitable that some fraction of those civilizations would send probes to explore other star systems. The logic is compelling. During the chaotic early stages of planetary system formation, countless objects are ejected into interstellar space. If even a tiny fraction of technologically advanced civilizations built spacecraft and sent them exploring, then over billions of years, the galaxy could become populated with such artifacts. Some would be derelict, their missions long since complete, or their parent civilizations extinct. Others might still be functional, still exploring, still gathering data. The probability of any given interstellar object being artificial might be low, but it wouldn't be zero. And this raises a profound question. If we're not willing to seriously consider the possibility that an anomalous interstellar object might be artificial, how would we ever recognize such an artifact if we did encounter one? If we reflexively explain away every unusual observation with increasingly exotic natural hypotheses, we might miss the very evidence we claim to be looking for. This concern motivated Loeb to do more than just write papers and books. In July 2021, he announced the Galileo Project. The Galileo Project and the Path Forward. The Galileo Project was conceived as a systematic, scientific effort to search for evidence of extraterrestrial technology, both in space and potentially near Earth. Unlike traditional SETI efforts, which listen for electromagnetic signals, the Galileo Project would search for physical artifacts. It would use advanced telescopes equipped with multiple sensors and artificial intelligence algorithms to continuously monitor the sky, looking for unusual objects and phenomena that might represent technology rather than natural astronomical bodies. The project had three main objectives. First, it would develop a network of telescopes to study unidentified aerial phenomena with scientific rigor, using standardized observation protocols and transparent data analysis. Whatever these mysterious sightings represented, whether conventional technology, atmospheric phenomena, or something more exotic, they deserved systematic investigation by scientists, rather than remaining the province of anecdotal reports and military secrecy. Second, the Galileo Project would search for additional Oumuamua-like interstellar objects. The next time such a visitor passed through our solar system, Loeb wanted to be ready. With advance warning and the right instruments, it might be possible to obtain high-resolution images, detailed spectroscopic data, even send a spacecraft to intercept the object for close-up examination. A single high-quality photograph, Loeb often said, would be worth more than 100 scientific papers filled with speculation. Third, the project would search for extraterrestrial satellites, artificial objects that might be orbiting Earth or other bodies in our solar system. If advanced civilizations had sent probes to explore stellar systems, Earth would be a logical target for investigation, given its obvious signs of life, and, more recently, its technological signatures. Perhaps such probes were already here, quietly observing, their presence masked by the growing population of human-made satellites and space debris. The announcement of the Galileo Project generated enormous media attention. Within weeks, donations totaling nearly $2 million had been secured from private individuals fascinated by the project's ambitions. Loeb assembled a team of astronomers, engineers, and other specialists from around the world, all willing to lend their expertise to what many considered a long shot, but a fascinating one nonetheless. The reaction from the broader scientific community was mixed. Some applauded the initiative, seeing it as a bold step toward legitimizing the search for extraterrestrial artifacts. If we're going to look for evidence of alien technology, they argued, let's do it properly, with purpose-built instruments, transparent methodology, and rigorous scientific standards. Others worried that the project would attract ridicule to serious astronomy, that it would divert resources and attention from more conventional research, that it represented a misallocation of effort and funding. Seth Shostak, senior astronomer at the SETI Institute, offered a measured perspective. While he compared the Galileo Project's search for alien artifacts in Earth's atmosphere to looking for mermaids or unicorns, unlikely quarry at best, He also acknowledged that Loeb deserved credit for his courage. Scientists should be grateful, Shostak suggested, that someone had the intellectual freedom and the determination to pursue ideas that most researchers would avoid. Even if the Galileo project found nothing extraordinary, it might develop new observational techniques and gather valuable data about atmospheric phenomena and small solar system objects. By early 2024, the Galileo project had deployed its first telescope arrays, sophisticated systems combining optical cameras, infrared sensors, and radar capabilities, all coordinated by artificial intelligence algorithms designed to distinguish ordinary phenomena from potential anomalies. The telescopes operated continuously, building vast databases of observations, watching for anything that defied conventional explanation. The project made all its data publicly available and committed to publishing all findings in peer-reviewed journals, ensuring transparency and inviting scrutiny. Meanwhile, the scientific debate over Oumuamua's nature continued. Each new theoretical paper proposing a natural explanation was met with critiques and counter-proposals. The hydrogen outgassing hypothesis, while elegant, faced challenges. Some calculations suggested that the proposed mechanism couldn't produce enough acceleration to match observations, or that the heat released during hydrogen release would alter the object's behavior in ways that weren't observed. Critics also pointed out that we had no direct evidence that cosmic ray processing of ice could produce the specific hydrogen-trapping structures the theory required. The nitrogen ice hypothesis faced its own difficulties. Nitrogen ice, while abundant on Pluto, is quite soft and would sublimate relatively quickly when exposed to starlight. Could a chunk of nitrogen ice really survive hundreds of millions of years, traveling through interstellar space? The erosion from impacts with dust grains and particles, the steady evaporation as the ice encountered starlight from distant stars during its journey, might have completely eroded such an object long before it reached our solar system. Loeb and his colleague Amir Siraj published calculations suggesting that a nitrogen iceberg would not survive the journey in a recognizable form. Every natural explanation seemed to require special conditions, specific circumstances that were possible but not necessarily probable. This didn't make them wrong, but it did highlight how unusual Oumuamua truly was. It was an object that challenged our categories, that didn't quite fit into our existing understanding of how small bodies in space behave and appear. Whether that strangeness pointed toward an artificial origin or simply toward the diversity of objects in the galaxy remained an open question. One thing became clear as the years passed: we needed more data. One interstellar object, observed for just a few weeks with telescopes not designed for such observations, simply wasn't enough to resolve the mystery. We needed to detect more interstellar visitors, to study them more carefully, to build up a statistical picture of what interstellar objects typically look like and how they typically behave. Only then could we properly assess whether Oumuamua was an extreme outlier or simply the first example we happened to notice of a class of objects that were more common than we realized. The universe, it seemed, would not keep us waiting forever. In 2019, less than 2 years after Oumuamua's discovery, astronomers spotted another interstellar visitor. This one, designated 2II Borisov, after its discoverer, Crimean amateur astronomer Gennady Borisov, looked much more like what astronomers expected from an interstellar object. It had a clear coma and tail, behaving exactly like a comet. Spectroscopic observations revealed water vapor, carbon monoxide, and other typical cometary ices. Its composition, was similar to comets from our own solar system, suggesting that the basic processes of planetary system formation and cometary composition might be universal. Borisov was, in a sense, reassuring. It showed that not every interstellar visitor would be as strange as Oumuamua. It demonstrated that at least some objects ejected from other planetary systems were entirely familiar, indistinguishable from objects in our own cosmic neighborhood. This made Oumuamua's peculiarities stand out even more sharply by comparison. Why was the first interstellar object we discovered so unusual, while the second was so ordinary? Then, in July 2025, came another discovery. The asteroid Terrestrial Impact Last Alert System, ATLAS for short, detected a third confirmed interstellar object. Initially designated 3I ATLAS, this new visitor immediately captured attention for reasons both scientific and, in some circles, alarming. Its orbital characteristics were unusual. Its trajectory was retrograde, meaning it orbited the Sun in the opposite direction from the planets, and its orbital plane was tilted only about 5 degrees from the ecliptic, the plane in which Earth and the other planets orbit. This near alignment with the planetary plane seemed remarkable. Out of all possible orbital orientations, the probability of an interstellar object randomly having an orbit so closely aligned with the plane of our solar system's planets was extremely low, less than 1% by simple geometric probability. Some researchers, including Loeb, noted that this alignment would make sense if the object had been deliberately aimed to pass near the inner planets. It would also put 3I ATLAS on trajectories that would allow relatively low energy transfers to Venus, Mars, and Jupiter, making it easier for a probe to send smaller craft or alter course to visit those worlds. Of course, the near alignment could also be simple coincidence. When you observe enough objects, unlikely configurations will occasionally occur just by chance. And retrograde orbits, while less common than prograde ones, were not unprecedented. Some comets from our own Oort cloud arrive on retrograde trajectories. The question was whether the totality of 3I ATLAS's characteristics warranted special attention, or whether it was simply another unusual but natural visitor. As with Oumuamua, scientists would have limited time to study this new object. Interstellar visitors pass through the inner solar system quickly, racing away at tens of thousands of miles per hour, and soon fade from view as their distance from Earth increases. Every hour of telescope time was precious, every observation potentially revealing new insights into the nature of these mysterious travelers from beyond. What do we really know? As we look back over the years since Oumuamua's discovery, several things have become clear. First, interstellar objects do visit our solar system, and they probably do so more frequently than we once thought. Improved telescopes and survey programs are detecting these visitors more reliably. Before 2017, we had detected 0 confirmed interstellar objects. Now, we have seen 3 in less than a decade. As survey telescopes become more sensitive and more comprehensive in their coverage of the sky, we will likely discover many more. Second, these objects are diverse. Oumuamua looked nothing like Borisov, which in turn may differ from 3I ATLAS and whatever future visitors we detect. This diversity tells us that planetary systems produce a wide range of small bodies, that the processes of ejection and evolution in interstellar space can create objects with very different properties. We should expect to be surprised by future discoveries, to encounter objects that challenge our assumptions and expand our understanding. Third, studying interstellar objects is hard. They arrive unannounced, moving fast, already on their way out of the solar system by the time we notice them. We get brief windows of opportunity to observe them before they fade into the darkness, too distant and too faint for even our most powerful telescopes to track. Advancing our understanding will require better detection, systems that can spot these objects earlier, while they're still approaching the sun, giving us more time to mobilize observational resources and plan follow-up studies. The challenge is formidable. Interstellar objects are small, often only a few hundred feet across at most. They don't emit their own light, only reflecting sunlight, and they're moving at tremendous velocities relative to the solar system. By the time they're close enough to be bright enough to detect with current survey telescopes, they've often already made their closest approach to the sun and are heading back out into the depths of space. We're essentially trying to spot fast-moving specks of rock or ice against the vast backdrop of the cosmos, and we have only the briefest of moments to study them before they're gone forever. The Vera C. Rubin Observatory, scheduled to begin full operations soon in Chile, promises to revolutionize our ability to detect these visitors. With its massive telescope and state-of-the-art digital camera, the largest ever built for astronomy, it will scan the entire visible sky every few nights, looking for anything that moves or changes. Its sensitivity will be orders of magnitude greater than current survey instruments. Astronomers estimate that once the Rubin Observatory is fully operational, we might detect one or more interstellar objects every few months, perhaps even more frequently. This prospect is exciting. Instead of having just a handful of examples to study, we'll be able to build up a substantial catalogue of interstellar visitors. We'll see the full diversity of objects ejected from other planetary systems. We'll be able to compare them statistically to determine what's typical and what's truly anomalous. We'll learn whether Oumuamua was a bizarre outlier or simply the first member of a class of objects that proved to be more common than we thought. But detection is only the first step. Once we spot an interstellar visitor, we need to mobilize observational resources quickly. Telescopes around the world need to be pointed at the object, coordinating observations across multiple wavelengths and instruments. Spectroscopy needs to be performed to determine composition. High-resolution imaging, to the extent possible given the object's size and distance, needs to be attempted. Radio telescopes might be employed to search for any unusual emissions. And all of this needs to happen quickly, within days or weeks, before the object fades from view. This requires planning and coordination on an unprecedented scale. The astronomical community needs to be ready to respond rapidly when interstellar objects are detected. Observing protocols need to be established in advance. Telescope time needs to be held in reserve for targets of opportunity. Analysis pipelines need to be prepared so that data can be processed and interpreted quickly while follow-up observations are still possible. It's a challenge that combines technical capabilities with organizational coordination, and it's something the field is only beginning to grapple with seriously. Beyond observation, there's the tantalizing possibility of actually visiting an interstellar object, sending a spacecraft to intercept it for close-up study. This is no simple task. By the time we detect these objects, they're typically already moving away from the inner solar system at high velocity. Catching up with them would require launching a spacecraft with tremendous speed, far exceeding what our current propulsion systems can readily achieve. Gravitational assists from Jupiter or the Sun could help, but the windows of opportunity are narrow, and the missions would take years or even decades to reach their targets. Several groups have studied the feasibility of such missions. Project Lyra, initiated by the Initiative for Interstellar Studies, examined whether it would be possible to send a spacecraft to Oumuamua. Their calculations showed that if a mission had been launched shortly after the object's discovery, using the most powerful rockets available and employing gravitational assists, it might have been possible to catch up with Oumuamua. but only after many years of travel. By the time any probe arrived, Oumuamua would be in the outer reaches of the solar system, far beyond Neptune, operating in the cold darkness where sunlight is weak and power generation difficult. For future interstellar visitors, the key will be early detection. If we could spot an object while it's still approaching the inner solar system, perhaps while it's still beyond Jupiter's orbit, we might have time to design, build, and launch an interceptor mission. Such a mission would need to be capable of matching the object's velocity, of rendezvousing with it rather than simply flying past in a high-speed encounter. It would need instruments capable of high-resolution imaging, spectroscopy across multiple wavelengths, perhaps even tools for collecting samples or measuring physical properties like density and composition directly. The technology for such missions is within our reach, or nearly so. We've successfully rendezvoused with comets and asteroids in our own solar system. The European Space Agency's Rosetta mission spent months studying Comet 67P Churyumov-Gerasimenko up close, even landing a probe on its surface. NASA's OSIRIS-REx mission collected samples from asteroid Bennu and returned them to Earth for laboratory analysis. These missions demonstrate that we can navigate to small bodies, match their motion, and study them in detail. Adapting these capabilities for interstellar visitors would be challenging, but not impossible. The main obstacles are time and money. Designing and building a spacecraft takes years under normal circumstances. Securing funding, assembling a team, developing and testing instruments, integrating everything into a working probe that can survive the rigors of space travel, all of this requires time and substantial resources. For a mission to an interstellar object to succeed, much of this work would need to be done in advance, ready to be activated when a suitable target is detected. The spacecraft might need to be built and waiting, stored in a clean room, ready for rapid integration of final components and launch on short notice. Such a capability would be expensive to maintain, but it might be the only way to ensure we don't miss opportunities to study these rare visitors up close. Some researchers have proposed even more ambitious concepts. Nuclear propulsion systems, either thermal or electric, could provide the high velocities needed to catch fast-moving interstellar objects. Solar sails or laser-driven light sails might enable extremely high-speed missions, potentially reaching velocities of tens or even hundreds of kilometers per second. These technologies are still largely in the development phase, but they represent pathways to making interstellar object intercepts more feasible. There's also discussion of preparing a spacecraft that could be launched on very short notice, perhaps within days or weeks of detecting a promising target. This rapid response concept would require pre-positioning resources, having rockets on standby, and accepting higher levels of risk in exchange for speed. The spacecraft might be less sophisticated than a traditional deep space probe, equipped with only essential instruments, optimized for fast deployment rather than comprehensive capabilities. But even a simple probe that could reach an interstellar visitor and take close-up photographs would be invaluable, providing data we could never obtain from Earth-based telescopes. It will also require missions capable of intercepting these objects, sending spacecraft to rendezvous with them for close-up examination. Several such mission concepts have been studied. The Initiative for Interstellar Studies examined Project Lyra, exploring whether it would be possible to send a spacecraft to catch up with Oumuamua using advanced propulsion systems and gravitational assists from Jupiter. The calculations showed it was technically feasible, but would require launching within a narrow time window and would take many years to reach the target. By the time any such mission could arrive, Oumuamua would be far beyond the orbit of Neptune, a tiny speck in the vast darkness between stars. For future interstellar visitors, advance warning would be crucial. If we could detect an object while it was still approaching the solar system, perhaps even before it reached Jupiter's orbit, there might be time to design, build, and launch an interceptor mission. Such a mission could obtain high-resolution images, conduct spectroscopic analysis across multiple wavelengths, perhaps even collect samples if the technology permitted. A single successful rendezvous could answer questions that decades of telescope observations couldn't resolve. As for Oumuamua itself, the object is, now beyond reach, racing through space toward the constellation Pegasus at about 59,000 miles per hour relative to nearby stars. In roughly 20,000 years, if it maintains its current trajectory and isn't perturbed by encounters with other stars, it might pass through another stellar system, becoming a brief visitor there as it was here. The beings of that system, if any exist and if they're paying attention, might detect it, puzzle over it, wonder about its origins just as we have. And what should we conclude about its nature? After years of debate, after dozens of scientific papers exploring every conceivable hypothesis, what is the most reasonable assessment? The honest answer is that we don't know. The data we have is insufficient to draw definitive conclusions. Oumuamua could be a highly unusual but entirely natural object, something nature created through processes we haven't yet fully understood. The hydrogen outgassing hypothesis, or the nitrogen ice hypothesis, or some other natural explanation not yet proposed, might correctly account for its observed properties. Or it could be artificial, not necessarily a functional probe, perhaps just a piece of debris, a fragment from some technological object that was torn apart by the forces of interstellar travel, or by a collision with another object billions of years ago, a piece of a light sail, or part of some other structure whose purpose we can't even imagine. The evidence doesn't definitively prove this interpretation, but neither does it definitively rule it out. This ambiguity is frustrating. We want clear answers, definitive conclusions. But sometimes the universe presents us with mysteries that can't be immediately solved. Questions that must remain open until we gather more evidence. What we can say is that Oumuamua was anomalous in multiple, independently verified ways. Its shape, its motion, its lack of visible cometary activity, despite showing acceleration consistent with outgassing, its tumbling rotation, all of these characteristics taken together made it unlike anything we had seen before. Whether that strangeness points to artificial origins or to the incredible diversity of natural objects in the cosmos is a question that future discoveries may help answer. Each new interstellar visitor we detect adds to our understanding. Each provides context for evaluating whether Oumuamua was a true outlier or simply the first member of a population that proves to be more varied than our limited experience suggested. The broader implications. The Oumuamua debate touches on something deeper than just one unusual object. It forces us to confront questions about how we do science, about what kinds of hypotheses we're willing to seriously consider, about the role of skepticism and open-mindedness in the scientific process. Science prides itself on following evidence, on being willing to overturn cherished beliefs when data demands it. Yet science is also practiced by humans, and humans have biases, preferences, comfort zones that influence how we interpret ambiguous information. The reluctance of many scientists to seriously consider an artificial origin for Oumuamua stems partly from legitimate scientific caution. Extraordinary claims do require extraordinary evidence, and we should be skeptical of conclusions drawn from limited data. Making grand pronouncements about alien artifacts based on a handful of observations of a distant, blurry object would indeed be premature. But does that skepticism sometimes shade into close-mindedness? Are we too quick to dismiss certain hypotheses simply because they make us uncomfortable or because they carry social stigma? The history of science is filled with examples of ideas that were initially rejected or ridiculed but eventually proved correct. Continental drift, the bacterial origin of ulcers, the existence of black holes, all faced significant resistance before evidence became overwhelming. The scientists who proposed these ideas were sometimes ostracized, their careers damaged by their willingness to challenge prevailing orthodoxies. In hindsight, we celebrate their intellectual courage, but in the moment, they were often viewed as troublemakers or cranks. Could the same pattern be playing out with the search for extraterrestrial artifacts? Are we too quick to explain away evidence, too willing to propose increasingly exotic natural phenomena, rather than seriously consider the possibility that we share the galaxy with other technological civilizations? Or is the skepticism appropriate, a necessary guard against wishful thinking and premature conclusions? These are not easy questions to answer, and reasonable people can disagree. What's clear is that the detection of genuine artifacts from an extraterrestrial civilization would be one of the most important discoveries in human history. It would fundamentally alter our understanding of our place in the universe. We would know definitively that we are not alone, that intelligence and technology are not unique to Earth. Such knowledge would raise profound new questions. Where did this civilization originate? Do they still exist? What can we learn from their technology? Are there messages embedded in the artifacts, attempts at communication? Should we try to signal our presence or maintain silence? The implications would extend far beyond science. Philosophy, religion, politics, culture, all would be affected by the confirmation that other minds exist among the stars. Our cosmic loneliness would end, replaced by the thrilling and perhaps terrifying knowledge that the universe is or has been inhabited by others capable of building, exploring, wondering. The paradigm shift would be complete and irreversible. Think about what such a discovery would mean for our understanding of ourselves. For all of recorded history, humanity has wondered whether we are alone in the cosmos. Philosophers have debated the question for millennia. Religions have offered various answers, some suggesting that humanity is unique and special, others leaving room for the possibility of other beings. Science fiction has explored countless scenarios of first contact, of meetings with alien civilizations, both benevolent and hostile. But we've never known. Not really. We've speculated, hoped, feared, imagined, but we've never had definitive evidence one way or another. The detection of an extraterrestrial artifact would change that. It would transform our relationship with the universe. We would know, beyond doubt, that the cosmos is populated with minds, that intelligence has arisen more than once, that the particular combination of chemistry and complexity that produced consciousness on Earth has occurred elsewhere. Such knowledge would raise as many questions as it answered. If the artifact came from a civilization that still exists, that might still be exploring and building and expanding their reach across the stars, then the possibilities become extraordinary. Could we communicate with them, learn from them, join some galactic community of civilizations? Or would the distances and timescales involved make such interaction impossible, condemning us to know they exist but never truly connect? And if the artifact came from a civilization that no longer exists, from a species that rose to intelligence and technology only to fall back into extinction, perhaps millions or billions of years ago, then the implications would be darker. It would suggest that technological civilizations, while possible, might also be fragile. That the path from simple life to spacefaring intelligence is traversable, but that the continuation of such civilizations over deep time might be uncertain. We would be confronted with our own mortality writ large, forced to contemplate not just our individual deaths or even the death of our species, but the potential transience of intelligence itself. Either scenario would fundamentally change human culture. Our art, our literature, our philosophy, our very sense of who we are would all be affected by this new knowledge. We would no longer be able to think of ourselves as the pinnacle of cosmic evolution, the only beings capable of contemplating the universe. We would become, instead, one among many, perhaps among countless civilizations that have arisen from the raw material of stars and planets. Our uniqueness would be diminished even as our cosmic context expanded to include others who, like us, emerged from matter and energy to ponder existence. Consider, too, the technological implications. If we could study an alien artifact closely, if we could examine its materials and construction, its propulsion system and design principles, what might we learn? Even a derelict probe from a civilization only slightly more advanced than our own could provide insights that leapfrog our technology forward by decades or centuries. New materials, new energy sources, new methods of space travel, all could potentially be reverse engineered from careful study of their creations. This possibility, while exciting, also raises concerns. Would such knowledge be shared openly, contributing to all humanity's advancement? Or would it be hoarded by nations or corporations, used to gain strategic advantages? Would the discovery unite humanity in a common quest to understand and respond? Or would it exacerbate existing divisions and conflicts? These are not idle questions. How we handle such a momentous discovery would reveal much about who we are as a species. And then there are the darker possibilities that must be considered. What if an alien artifact, far from being a derelict or passive probe, proves to be something more active? The so-called dark forest hypothesis, popularized by science fiction writer Liu Cixin, suggests one resolution to the Fermi paradox, the question of why we haven't yet detected alien civilizations despite the apparent likelihood of their existence. Perhaps, the hypothesis goes, the universe is like a dark forest where predators lurk. Civilizations stay quiet, hiding their presence, because advertising your existence in a cosmos full of potentially hostile intelligences might be suicidal. If this grim view is correct, then an alien probe entering our solar system might not be a peaceful explorer, but something far more sinister. A von Neumann probe, perhaps, a self-replicating machine designed to explore and potentially consume the resources of stellar systems it encounters. Or a weapon, sent by a civilization that views other intelligences as threats to be eliminated before they can become dangerous. These scenarios, while speculative, can't be entirely dismissed. We simply don't know what motivations might drive other civilizations, what philosophies might guide their actions, what threats they might perceive or pose. Most scientists, including Loeb, believe that if we did detect an alien artifact, it would most likely be benign. Civilizations capable of interstellar exploration have presumably survived their own technological adolescence, learned to manage the destructive technologies that threaten young civilizations like our own. They've achieved some level of wisdom and stability, qualities necessary for long-term survival on cosmic timescales. But this is speculation. We have a sample size of one civilization, our own, and our track record of wisdom and restraint is decidedly mixed. The point is that the detection of extraterrestrial artifacts wouldn't just be an abstract scientific discovery. It would have immediate practical implications for how we think about our future, how we assess threats and opportunities, how we make decisions about our own exploration of space and our signals to the cosmos. It would force us to grow up, in a sense, to recognize that we're not the only players in this cosmic game, that our actions might have consequences we haven't fully considered, that the universe is a place of wonders and possibly dangers we've barely begun to comprehend. But such a discovery requires evidence, clear and compelling evidence that can withstand intense scrutiny. A single ambiguous object, however strange, is not enough. We need multiple lines of evidence. We need reproducible observations. We need data so strong that natural explanations become untenable. The bar is high, as it should be, because the conclusion is so extraordinary. This is why the Galileo project and similar efforts matter. By systematically searching for artifacts, by deploying instruments specifically designed to detect and characterize unusual objects, we increase the probability that if such evidence exists, we will find it. And equally importantly, if we search thoroughly and find nothing, that non-detection itself would be informative. It would help us estimate how common or rare technological civilizations might be, how frequently they might send probes to explore other stellar systems, how long such artifacts might survive in the harsh environment of interstellar space. The philosopher of science Karl Popper argued that good scientific hypotheses must be falsifiable, that they must make predictions that can be tested and potentially proven wrong. The hypothesis that interstellar artifacts occasionally visit our solar system is eminently falsifiable. We can search for such objects systematically. We can define what characteristics would constitute strong evidence of artificiality. We can deploy instruments and develop observation protocols specifically designed to detect such evidence if it exists. If, after decades of systematic searching with increasingly sophisticated instruments, we find no compelling evidence of extraterrestrial artifacts that would constitute strong evidence against the hypothesis. Not absolute proof. The absence of evidence is never quite the same as evidence of absence, but it would significantly reduce the probability that such artifacts are common in our stellar neighborhood. Conversely, if we do find such evidence, if we detect objects whose characteristics cannot be plausibly explained by any natural process, then the hypothesis would be supported, potentially even confirmed. The Oumuamua debate and the scientific method. The passionate debates surrounding Oumuamua reveal something important about how science works, and perhaps more importantly, how it should work. Science isn't just a collection of facts or a set of techniques. It's a process, a way of thinking about the world that values evidence over authority, that welcomes debate and disagreement, that constantly questions and refines its own conclusions. At its best, science is self-correcting, able to abandon cherished theories when they no longer fit the data, able to embrace new ideas when evidence demands it. But scientists are human, and humans are prone to biases, to emotional attachments to their theories, to social pressures that can influence how they interpret ambiguous evidence. The history of science is filled with examples of good ideas that were initially rejected because they conflicted with prevailing beliefs. Continental drift, the notion that Earth's continents slowly move across the planet's surface, was ridiculed when Alfred Wegener first proposed it in the early 20th century. It would take decades and the accumulation of overwhelming evidence before the theory of plate tectonics became accepted. Similarly, the idea that bacteria could cause stomach ulcers was dismissed when first proposed by Australian physicians Barry Marshall and Robin Warren in the early 1980s. The medical establishment believed that ulcers were caused by stress and diet, not infection. It took years of research, including Marshall's dramatic decision to deliberately infect himself with the bacteria to prove his point, before the idea gained acceptance. Marshall and Warren eventually won the Nobel Prize for their discovery, but they faced years of skepticism and resistance first. These examples remind us that scientific consensus, while usually a good guide to truth, is not infallible. sometimes the consensus is wrong. Sometimes the maverick pushing an unpopular idea turns out to be correct. The trick is distinguishing between legitimate scientific rebels with genuine insights and cranks promoting nonsense. This is never easy, particularly when the evidence is ambiguous and incomplete, as it invariably is at the frontier of knowledge. With Oumuamua, we're confronting exactly this challenge. We have limited data about an unusual object. Multiple hypotheses have been proposed to explain it, ranging from conventional to exotic, from natural to potentially artificial. How do we evaluate these competing explanations? How do we decide which deserves serious consideration and which can be dismissed? What standards of evidence should we apply? There's no simple formula, no algorithm that can provide definitive answers. We have to rely on scientific judgment, on our collective assessment of what's plausible and what's not, on our estimation of probabilities and our weighing of different types of evidence. This is inherently subjective to some degree, influenced by our background knowledge, our experiences, our assumptions about the universe. Two equally qualified scientists examining the same data might reach different conclusions about what it means or which hypothesis it best supports. This subjectivity doesn't mean science is just opinion or that all interpretations are equally valid. Evidence still matters. Logic still matters. The requirement that theories make testable predictions, that they be consistent with other well-established knowledge. These constraints significantly narrow the range of acceptable explanations. But within those constraints, there's still room for disagreement, for different assessments of probability, for different judgments about what counts as a good explanation. The debate over Oumuamua illustrates this perfectly. No one disputes the observations themselves. The object's trajectory, its brightness variations, its lack of visible coma. These are facts, verified by multiple independent observers using different instruments. What's disputed is the interpretation. What do these facts tell us about the object's nature? Are they consistent with a highly unusual but natural object? Or do they point towards something artificial? Reasonable people, looking at the same evidence, come to different conclusions. Some find the natural explanations perfectly adequate, perhaps requiring some refinement but basically sound. Others find them unsatisfying, too contrived, requiring too many special conditions to work. Some think the artificial hypothesis is worth serious consideration. Others think it's wildly speculative, unsupported by sufficient evidence. And still others occupy a middle ground, acknowledging uncertainties on both sides, waiting for more data before committing to any strong position. This diversity of opinion is actually healthy for science. It ensures that different possibilities are explored, that assumptions are questioned, that no single interpretation becomes dogmatically entrenched before the evidence justifies it. The danger comes when disagreement turns into dismissal, when proponents of different views stop listening to each other, when debate degenerates into personal attacks or accusations of bad faith. Sadly, the Oumuamua controversy has sometimes crossed that line, with both sides occasionally characterizing the other in uncharitable terms. Loeb, for his part, has argued that he's simply following the evidence and that his critics are letting social stigma cloud their judgment. His detractors counter that he's overstating the case for artificial origins, that he's promoting speculation beyond what the data justifies, perhaps seeking publicity or championing a cause at the expense of careful analysis. Both sides can marshal arguments and evidence to support their positions. Both sides include serious, accomplished scientists with deep expertise in relevant fields. The resolution, if it comes, will likely emerge from additional observations. As we detect more interstellar objects and study them more carefully, patterns will emerge. We'll learn what's typical and what's truly anomalous. We'll develop better theories of how different types of objects form and evolve during their journeys through interstellar space. We'll refine our ability to distinguish between natural and potentially artificial objects based on their observable characteristics. The controversy over Oumuamua may fade as we gain more context, or it may intensify if we encounter additional objects with similar puzzling properties. What's important is that we keep looking, keep gathering data, keep refining our theories, and testing our hypotheses. Science progresses not through pronouncements from authority, but through the patient accumulation of evidence and the testing of ideas against reality. The Oumuamua debate, for all its controversies and heated exchanges, represents science working as it should. People with different perspectives are examining evidence, proposing explanations, critiquing each other's ideas, and gradually working toward a better understanding of the truth. The Fermi paradox and our place in the cosmos. The Oumuamua debate also connects to one of the most profound questions in all of science. Where is everybody? This question, famously posed by physicist Enrico Fermi during a lunch conversation in 1950, has come to be known as the Fermi paradox. If intelligent life is common in the universe, if technological civilizations arise frequently among the trillions of planets orbiting the hundreds of billions of stars in our galaxy alone, then why haven't we detected any clear signs of their existence? Why do the skies seem so empty of other minds? The paradox arises from the apparent contradiction between high estimates of the probability of extraterrestrial civilizations and the complete lack of evidence for them. The galaxy is old, about 13 billion years. Stars and planets have been forming for most of that time. Life on Earth arose relatively quickly once conditions became suitable, within the first billion years of our planet's history. If similar processes occur elsewhere, and if even a tiny fraction of life-bearing worlds eventually develop intelligent technological species, then the galaxy should be teeming with civilizations, many of them millions or billions of years older than humanity. Given that kind of head start, some of these civilizations might have developed technologies far beyond our current capabilities. They might have colonized their local stellar neighborhood, spreading from star to star. They might have built megastructures visible across interstellar distances. They might have sent self-replicating probes to explore every corner of the galaxy. Yet we see none of this. Our telescopes detect no evidence of stellar engineering, no signs of massive artificial structures, no clearly artificial signals in the radio or optical spectrum. The universe appears, at least on first inspection, to be devoid of other technological civilizations. This apparent absence has led to numerous proposed solutions to the Fermi paradox. Perhaps intelligent life is much rarer than we think, requiring such an unlikely sequence of events that Earth might be one of only a handful of worlds where it has arisen. Perhaps technological civilizations tend to destroy themselves shortly after developing advanced technology, through war, environmental collapse, or some other catastrophe. Perhaps they exist but choose not to expand or advertise their presence for reasons we can't fathom. Perhaps they're so advanced that we simply don't recognize their artifacts or activities as artificial any more than an ant would recognize a smartphone as technology. Or perhaps, and this is where Oumuamua enters the discussion, we simply haven't looked carefully enough. Maybe the signs are there, but we've been looking for the wrong things or in the wrong ways. Traditional SETI has focused on detecting radio or optical signals, deliberate transmissions from other civilizations attempting to communicate across the stars. But what if advanced civilizations don't communicate via radio? What if they use technologies we haven't developed or can't detect? What if the way to find evidence of their existence is not to listen for messages, but to look for their artifacts. This is where the study of interstellar objects becomes particularly significant. If even a small fraction of technological civilizations sends probes to explore other stellar systems, and if these probes survive for long periods in interstellar space, then the galaxy might contain a substantial population of such artifacts. We wouldn't need to detect civilizations actively trying to communicate. We just need to recognize their hardware when it passes through our solar system. The statistics are intriguing, if speculative. Consider that there are perhaps 400 billion stars in our galaxy. If even 1 in a million develops a technological civilization, that's 400,000 civilizations. If each sends out just 1,000 probes during its existence, exploring nearby stellar systems, that's 400 million probes total. Spread over the volume of the galaxy and billions of years of operation, the density wouldn't be high, but it wouldn't be negligible either. Occasional encounters would be expected. Of course, these numbers are largely guesswork. We don't know how common technological civilizations are, or how many probes they might build, or how long such probes survive in the harsh environment of interstellar space. But the point is that the scenario isn't absurd. It's at least plausible that artifacts from other civilizations could occasionally visit our solar system. And if that's the case, then objects like Oumuamua deserve careful scrutiny. The Fermi paradox also highlights the challenges of searching for something when you don't know quite what you're looking for. We have one example of technological civilization, our own, and we tend to assume that others might be similar. But this assumption could be wrong. Other civilizations might develop along radically different trajectories, might have priorities and values and capabilities we can't imagine. Their technologies might be so different from ours that we wouldn't recognize them as technologies at all. This is why the search for extraterrestrial intelligence needs to be broad and diverse, why we need to look in multiple ways for multiple types of signatures. Radio SETI is valuable, looking for deliberate signals. Optical SETI, searching for laser pulses, adds another dimension. The search for technosignatures, looking for evidence of engineering on planetary or stellar scales, provides yet another approach. And now, the systematic study of interstellar objects, looking for artifacts that might be visiting our solar system, adds one more tool to the kit. No single approach is guaranteed to succeed, but by pursuing multiple strategies, by casting a wide net, we increase the probability that if evidence of other civilizations exists within our reach, we'll eventually find it. And if we search thoroughly and find nothing, that itself tells us something important about our cosmic context. It suggests that we might be more alone than we hoped, that intelligence and technology might be rare in the cosmos, that the emergence of beings like us might be a precious and fragile thing. A cosmic perspective. As Oumuamua continues its journey through the darkness between stars, as the debates about its nature continue, as new interstellar visitors arrive and depart, it's worth stepping back to consider the broader context. We live in a galaxy containing hundreds of billions of stars. Each of those stars potentially hosts planetary systems, worlds where the same laws of physics and chemistry that govern Earth apply equally. The same processes that led to the emergence of life on our planet could be occurring on countless other worlds scattered across the galactic disk. We don't know how common life is, or how frequently it develops intelligence and technology. The answers to these questions remain among the deepest mysteries in science. But we do know that the ingredients for life, the basic building blocks, are abundant throughout the universe. Water is everywhere. Organic molecules form readily in space. The conditions that led to life on Earth are not unique or even particularly special. If intelligent life exists elsewhere, And if even a small fraction of such civilizations develop spacefaring technology and the inclination to explore, then over billions of years, the galaxy could become populated with their artifacts. Probes sent out to study distant stars, monuments built to outlast their creators, debris from failed missions, or from civilizations that destroyed themselves or simply faded into extinction. The sum total of billions of years of technological activity by multiple civilizations would leave traces, signatures that patient observers might detect. We are only now developing the capability to look for such evidence systematically. Our telescopes are becoming sensitive enough to detect small objects at great distances. Our artificial intelligence algorithms are sophisticated enough to distinguish unusual phenomena from the normal background of astronomical observations. Our understanding of solar system dynamics and orbital mechanics is mature enough to recognize when something doesn't fit expected patterns. In this context, Oumuamua represents a beginning, not necessarily a definitive discovery of extraterrestrial technology. The evidence remains ambiguous and contested, but a beginning nonetheless. It showed us that interstellar objects do visit our solar system. It demonstrated that some of these visitors can be highly unusual, challenging our expectations and defying easy categorization. It sparked a conversation about how we search for evidence of other civilizations, about what kinds of evidence we should look for, about how we should respond when we encounter something we don't immediately understand. Perhaps most importantly, Oumuamua reminded us that the universe still holds mysteries, that despite centuries of scientific progress, we have not exhausted the capacity of the cosmos to surprise us. There are still discoveries to be made, still phenomena to be understood, still questions whose answers might fundamentally change how we see our place in the vastness of space and time. As you lie there now, letting these thoughts settle, consider what it would mean to know for certain that we are not alone. That somewhere out there, perhaps looking up at their own night sky, perhaps contemplating the same questions we contemplate, other minds exist, other beings who wonder, who explore, who build and create and search for meaning in the darkness between stars. The universe would feel different, wouldn't it? Less lonely, more populated with possibility. Or consider the opposite conclusion, that after exhaustive searching, after decades of looking, we find no evidence of other technological civilizations. That perhaps we are alone, or at least alone in our corner of the galaxy, separated from any neighbors by distances so vast that contact, even detection, is impossible. That conclusion, too, would be profound. It would make us precious, the only known bearers of consciousness and intelligence in a cosmos that for all its grandeur seems empty of other minds. Either way, the search continues. New telescopes scan the skies. Artificial intelligence algorithms sift through mountains of data, looking for anomalies. Teams of scientists debate hypotheses, propose new observations, refine their understanding of what's possible and what's probable. And somewhere out there, beyond the orbit of Neptune, beyond the Kuiper Belt, beyond any realm we can directly observe, Oumuamua tumbles through the darkness, keeping its secrets, heading toward encounters we can only imagine. Closing reflections. The story of Oumuamua is not over. It continues in the work of scientists who study interstellar objects, in the ongoing debates about its nature, in the missions being planned to intercept future visitors. It continues in the broader search for life beyond Earth, in our growing understanding that we inhabit a universe rich with potential for discovery. What began as a point of light detected by a telescope in Hawaii has become something larger, a symbol of humanity's quest to understand our cosmic context. Are we alone? Have others traveled between the stars as we now contemplate? When we look at the night sky, Are we seeing only lifeless matter following predictable physical laws? Or might some of those distant points of light harbor civilizations, perhaps far more ancient than our own, perhaps with knowledge and capabilities we can barely imagine? We don't yet know the answers. Oumuamua didn't provide the definitive evidence that would settle these questions once and for all. But it opened doors, started conversations, sparked imaginations. It showed us that the universe still has surprises to offer, that our models and theories, however sophisticated, don't capture the full diversity of what exists out there in the cosmic dark. And that's perhaps the most important lesson: to remain curious, to stay open to possibilities while maintaining rigorous standards of evidence, to search patiently, knowing that the universe reveals its secrets slowly, on timescales that sometimes exceed human lifespans, to accept that some questions may remain unanswered for years or decades, held in suspension until technology advances and more data becomes available. As this story comes to a close, as your breathing slows and your mind drifts towards sleep, let yourself feel that sense of cosmic possibility. Somewhere in the vastness of space, other worlds orbit other stars. On some of those worlds, perhaps life has emerged, evolved, developed intelligence. Perhaps they too gaze at the stars and wonder. Perhaps some have already taken their first steps into space, sent their first probes to explore neighboring systems, looked with wonder at objects that wandered into their corner of the galaxy from the darkness between stars. We are part of that cosmos, made of the same elements forged in ancient stars, governed by the same physical laws, possessed of the same drive to explore, to understand, to find meaning in the patterns we observe. Whether we are alone or surrounded by others, we are children of the universe, temporary configurations of matter that have somehow become capable of contemplating our own existence and wondering about the existence of others. Oumuamua came and went, a visitor from beyond, a mystery that may never be fully solved. But in its brief passage through our solar system, it reminded us of truths we sometimes forget: that the universe is larger and stranger than we imagine, that mysteries remain to be explored, that the greatest discoveries may still lie ahead, waiting for us to develop the tools and the courage to find them. If you've enjoyed this exploration of one of the great cosmic mysteries of our time, please consider subscribing to the Mind Whisper channel for more journeys through the wonders of science and space. Leave your thoughts in the comments below. What do you think Oumuamua was? A natural object from another star? An alien artifact? Something we haven't even considered yet? The conversation continues, and your voice is part of it. Until next time, keep looking up, keep wondering, keep searching for answers to the questions that have captivated humanity since our ancestors first gazed at the night sky and asked, "What else is out there? And are we alone?" Sweet dreams. The stars are waiting. Stars are waiting.